Hey everybody, welcome to the Pipeline Integrity Show. I'm your host, Hussain Fadhel. We just finished off a wonderful interview with Colin Scott, where we discussed cracking in the world of pipelines. This is part one of a two-part series. Hope you enjoy the interview and see you soon.
Hey everybody, welcome back to the Pipeline Integrity Show. Our guest on today is Colin Scott. Welcome to the show.
Thank you very much. Glad to be here.
Perfect. So we're going to be talking about cracking in the world of pipelines. This is part one of our two-part series with Colin. Colin, if you could start us off with an introduction, please.
Okay, certainly. Thank you. My name is Colin Scott. I'm a pipeline integrity engineer. Right now I'm based out of Calgary, but I'm not actually from out west. I'm originally from out east. I went to Queen's University for undergraduate and studied material science and metallurgical engineering. And then the job situation wasn't too good when I graduated, so I ended up going back to graduate school at McMaster University. And there I studied more materials engineering, and my focus, my specialization was on fracture mechanics. So that's kind of how I first started getting involved in crack management. The first job that I had when I finished graduate school was for a company in Toronto, where I was doing consulting for the nuclear industry. So it's a little bit different from this, but the nuclear industry has its own piping issues. I was looking at cracking in feeder pipes. I was looking at cracking in zirconium alloys. Different ball game, but I learned a lot of things that became useful for the pipeline integrity industry. So after about 3 years of nuclear work, I ended up moving south to the United States. I moved to Ohio and ended up working with the DNV group out of Columbus, Ohio, just near Columbus in Dublin, Ohio. And that's a group that's really a hotbed of a lot of pipeline integrity work. Some of the people there are cast-offs from the old Brittle Institute, and it seems to attract a lot of people that are in this business. I spent about 8 years with DNV. I worked with the research group. I worked with a group called Litigation Support Services Group, and I worked with the Failure Investigation Group. And then after about 8 years, I'd sort of been there, done that, and needed to change. So I ended up moving back to Canada, and I ended up working for 3 years in Edmonton with Enbridge liquid pipelines. This was before they'd acquired Spectra, so most of my knowledge from there is on the liquids side of things. I worked with the Integrity Planning Group, and for 2 years out of my 3 years there, I was the subject matter expert for the crack management program. And then after about 3 years, I decided to take a jump. I came back into the consulting world, and I worked for 2 years with Iris NDT Engineering Services. Unfortunately, with the oil and gas business not doing so well and COVID and such, I was cut loose back in March. So right now I'm an independent, but working on a few things, and we'll see what happens next. So that's me in a nutshell.
Excellent. Thank you for that. So yeah, our theme today is the world of the cracking in the world of pipelines. And why don't you get us started us off with the different types of cracking in the world of pipelines. What do we see in terms of fatigue, environmental cracking, and the different types of cracking that we see, and perhaps maybe some of the mechanisms that cause them?
Sure. In the crack management world, in pipeline integrity, there's really sort of two broad buckets that we think about. One is fatigue cracks, and the fatigue cracks are more common in the older vintage lines, the 1950s, 1960s vintage lines, and it's going to be more common in liquids lines. The second bucket that we typically look at is stress corrosion cracking, and that can be more common in some of the gas lines, and that's going to be a little bit later in vintage. That seems to occur in the 60s, 70s, and 80s. So we've got a couple little time differences there. Now, when I say fatigue crack, really what I mean is crack growth associated with microscopic defects along long seam welds. When you look back in the 50s and 60s, the electric resistance weld technology that was used by all the pipe mills was really not as good as it is today. They didn't have the same QA standards. They didn't have the same understanding. And so when pipe joints were made back in the 50s and 60s, they tended to have a lot of microscopic flaws along the longitudinal seam. So you hear the term of lack of fusion or a cold weld, or you'll hear the term hook flaws. Now, the problem with those is that they can potentially lead to crack growth. They can create cracks, and you can get fatigue crack growth in the pipelines. Now, with the fatigue mechanism, essentially that comes down to a repeated pressure cycle. With a liquids line, if you think about it, it's not compressible. So when you turn those pumps on, the liquid cannot compress itself, so it ends up putting stress into the pipe. If you turn the pumps off, all of a sudden the stress goes down. So as you're operating your pipeline, you're going to high pressure, low pressure, high pressure, low pressure, up and down, depending on the details of your particular line. And what happens is if you've got microscopic defects along the long seam weld, they're going to feel an alternating high stress, low stress, high stress, low stress. And the high stress there is going to cause the crack tips to undergo some yielding, some ductility, and that's going to cause some work hardening of the material. And as you go back and forth, higher and lower stresses, you get a crack that will just kind of sneak its way through that zone. And if it gets deep enough, it can end in a really bad day. So that's something to keep an eye on. Now, with trying to deal with fatigue, the best way to deal with any one of our integrity problems, as you know, is prevention is better than a cure, right? If you can prevent things up front, you should do that. When you look at the 50s and 60s vintage pipelines, they didn't really have great QA. They didn't have great knowledge in how to prevent the defects. And that's something that we've learned a lot from. If you look at a modern pipe mill will typically have much better QA processes than they did 60, 70 years ago. And you're just not going to get the same sorts of defects that you are along the long seam weld. Typically in a pipe mill, there will be a pipe mill hydrostatic test where the pipe is filled full of water and pressurized. If there are any defects in there, it's going to pop right there in the pipe mill in a controlled environment. So that's one way to get rid of your defects. Another thing that they do in the pipe mill is to do an ultrasonic test where they put an ultrasonic scanner along the long seam and they look for any reflections that might be indicative of a defect. If a pipe passes its pipe mill QA, then it's going to be sent out to the field and put into the pipeline. It's going to be welded in with girth welds, and then when everything is welded up, there's typically going to be a commissioning Hydra test. If the pipeline passes the commissioning Hydra test, then you've got a pretty good sense that there aren't any really, really nasty flaws in the pipeline. And so that's one way to mitigate your fatigue right up front. The second thing is to try and avoid having pressure cycling. You might have a pipeline where it's really tempting to just turn it on, turn it off, batch processing, but that's really going to cause you a lot of problems. The really damaging thing about fatigue is that crack growth is, in very simple terms, proportional to the pressure cycling cubed, which means if you have a big pressure cycle, it's big to the power of 3, crack growth gets really, really serious. And that also tells us that we're going to tend to have much more fatigue issues right at the upstream end of the pipeline rather than the downstream end. If you've got a section of pipe right next to the discharge pumps, you're going to have very, very high pressure up at maximum operating pressure. If you go to the downstream end, it's going to be a lot lower because the next section will be a lower suction pressure. In very, very simple terms, if you assume that your pressure drops approximately halfway along the line, if you think about it, half cubed is 1/8, and so you would expect that halfway down the line, your crack growth would be 1/8 as quick, just in very simple broad brush terms. So there really is a focus on the upstream end of things. So
yeah, and just to ask there, gas companies often they'll suggest almost that they don't have to worry about fatigue. Is that true? Is just because they have more like line pack and they just sort of keep the pressure the same all the time, or because they don't really have batching process, but they still have to consider it, or what would you advise?
Well, I think that this is one of those things where it's a potential threat, but for a gas operator, it's going to be a lot lower on the list. In the pipeline business, you know that every single pipeline out there has its own characteristics, both good characteristics and bad characteristics. And it comes down to people like us and the other people in the business to take a look at each individual line, look at the characteristics of it. Is it old? Is it new? Good coating, bad coating, liquids, gas, pressure cycling? And I think it's our responsibility to have a good think about things and figure out which one of the threats are going to be a bigger problem for which line and which ones are not going to be a bigger threat. So for the gas lines, like you say, pressure cycling is not the same, and so the fatigue issue is going to be a lot lower on the list. The gas is compressible, so when you turn on those gas compressors, you have to, wait for several minutes or hours before the pressure actually gets up to a point where you're going to be operational or where you'd have a problem with fatigue. So it tends to be a lot less of a problem. When it comes to crack growth business, some of the gas operators will tend to focus a lot more on stress corrosion cracking. So that's kind of our second pile, if you want to move to that, or do you have any more questions on fatigue?
No, that's great. Thank you.
Okay. So stress corrosion cracking is a difficult one. Typically, you need three things for stress corrosion cracking to occur. You need a susceptible material, you need to have very high stress, and you have to have a corrosive environment. If you have all three of those and all the stars are completely misaligned for you, it can be a stress corrosion cracking issue. Now, stress corrosion cracking has got a different mechanism. It's not just about pressure cycling, and it's not just about having some plasticity at the crack tip that's sort of edging a crack along. With stress corrosion cracking, you have electrochemical reactions occurring at the crack tips. So things get a little bit different, and so it's different in the way that you control it. Now, I think even the experts debate what the actual mechanism is at the crack tip. Sometimes you'll hear the term like the film rupture model. And with that, the thinking is that right at the crack tip, you've got electrochemical reactions going on. You form an oxide or possibly a hydroxide at the crack tip. And that's going to be very, very brittle. And what will happen is as your pipe is stressed, that brittle layer is going to crack through and reveal bare material. And then that next bare material in line, it will also suffer from oxidation or hydroxide formation. It'll crack. And so you'll have this sequential sort of cracking and forming of a film. So that's one mechanism. The other mechanism that sometimes comes into the conversation is hydrogen generation and hydrogen getting pulled into the crack tip. The problem with that is that if you have hydrogen up in your crack tip, the hydrogen can get into your atomic lattice, and it can disrupt the movements of dislocations. And so you're really embrittling the material right at the crack tip. You're not allowing it to yield and absorb energy. So sometimes you'll hear about a hydrogen-based mechanism. So it's a little bit different from what we have with fatigue. Now, with fatigue, I mentioned that there's generally a cubic relationship with pressure cycling. If you do similar sorts of studies with stress corrosion cracking, the thinking is it tends to be not cubic, but a fairly linear relationship. So it turns into a different ballgame. What makes things really particularly tricky for the gas people is because the gas is compressible and because they don't have quick ups and downs, their pressure cycling tends to be a lot slower. And stress corrosion cracking is sensitive to the speed of your pressure cycles. If you were to have a really, really quick pressure cycle, things would, for all intents and purposes, be fatigue. But once you do it slower, those corrosive mechanisms, they have more of a chance to sort of take their time and do their chemistry and make things worse. If you look at some of the models that are available in predicting SCC crack growth rates, you'll find that a lot of them will have a cycling frequency component to them that kind of makes things a little bit different. Stress corrosion cracking is kind of a mysterious beast, even for the people that have studied it for years and years, and I don't think anybody's got all of the answers. So when it comes to mitigation, we need to do the best we can. Just like the fatigue, preventing stress corrosion cracking comes down to prevention is better than a cure. And there are, I guess, three things that we can think about. The first is studies have shown that there seems to be a susceptibility to stress corrosion cracking from pipe mills that have a lot of residual stresses in them. One of my former bosses did a pretty extensive statistical study where he found that some of the pipe mills in the US and Canada have no SCC problems reported. Some of them have got enormous SCC problems reported. And statistically speaking, it's at the point where there are going to be some operators that are going to look at the good list and look at the bad list and either not worry about it or worry about it a lot. So that comes down to how the pipe is made and how much residual stress gets put into the pipe wall, because that's really one of the key drivers of initiating stress corrosion cracking. The second thing we can think about is coatings. There are several different coatings that have been used over the pipeline integrity management history, and some are really good and some are really bad. At the very bad end of the spectrum is polyethylene tape coat. That was used in the 70s and 80s, and that is just the poster child of what not to do. It's kind of the equivalent of taking a big roll of Scotch tape and just kind of doing that to your pipeline. PE tape coat has got a nasty history of significant disbondment. It just doesn't stick well to the pipe. As the pipe is in operation, it flexes, it moves around a little bit. You may have some freeze-thaw type stuff going on, and as your pipeline moves, that tape kind of gets pushed and pulled and yanked in different directions, and that allows moisture in. So once you get,
I say that tape coating is the reason why we all have jobs and such nice integrity teams exist, right?
Yeah, pretty much, depending on where you're based. Yeah. So one of the tricky things with tape coat is not only does it disbond and allow moisture to get in under the coat, but the tape itself can shield your cathodic protection system. So you might have a cathodic protection system in place to try and prevent corrosion, and that can help you mitigate against SCC, but your PE tape coat can actually cause some shielding because of its insulative properties. So you might think that your cathodic protection is helping, but it really isn't. So for anybody that can completely avoid PE tape, it's not used anymore to my knowledge, and that's really good for us. Now that tape coating tends to be more commonly associated, my understanding is, with near neutral pH SCC, and it's typically more common in Canada. The second type of coating you sometimes see is coal tar or asphalt enamel, and that's kind of it's kind of moderate when it comes to stress corrosion cracking. That tends to be a little bit more common down in the United States. It's going to be more common in 50s and 60s vintage pipelines. And it's more commonly associated with high pH SCC or classical SCC. There's two flavors. If my memory serves me, I think asphalt enamel is slightly worse than coal tar, but those ones are kind of at the middle of the road. If you look at the more modern coatings that we have now, a lot of what we see is a fusion bonded epoxy is very common in some of the larger diameters. If you go to some of the smaller diameter pipelines, you'll get a 2-layer polyethylene, or sometimes you'll hear it referred to as yellow jacket. Those coatings are very good. Fusion bonded epoxy is the kind of the poster child of everything good. It's the gold standard in preventing stress corrosion cracking. The 2-layer polyethylenes are very, very good, though I have come across a couple of situations where there are problems with the girth weld joints because the wrap that's put over that 2-layer polyethylene has to be done exactly right. If you have somebody that's applying that coating at the joint and they're not trained up properly, or I don't know, maybe it's a Friday afternoon and they've got one eye on their watch and they're, the pub is down the road, you might run into some problems. So
yeah,
that's
plenty of I think instances of shrink sleeve disbondments, or basically they're just floating there, and I think I've seen a few failures at girth welds, corrosion essentially because of shrink sleeves
that
not
can be a problem
properly.
Yeah. So there's the corrosion side of things, and then as I mentioned, you've got a cathodic protection system that is always going to be in place to prevent corrosion, and that can mitigate against your stress corrosion cracking. If you have a PE tape coat, though, you can have shielding, which essentially blocks that current from getting to the pipe. Another tricky thing to think about with the cathodic protection is you've got a pipeline that's several kilometers long, and you've got your anode beds lined up, and you've got your rectifiers. But you can't guarantee what the potential is at every section along the pipeline. And stress corrosion cracking tends to be very, very sensitive to certain potentials. There are certain just hot potentials where everything goes sideways. It depends on whether you've got a near neutral pH SCC or you've got high pH, the classical SCC. There are kind of these magic potentials that you really want to steer clear of. And that's not always going to be possible, because essentially if you've got a long pipeline, there's essentially going to be a sort of a potential variation from one end to the other, and it's pretty likely that there's going to be somewhere in that region that is just at one of those hot spots. So that can turn into a problem there. It keeps guys like you and me busy on keeping on top of these sorts of things.
So I wanted to ask about I know we're going to talk more about this tomorrow, but can you maybe glaze over some of the different crack assessment models we have in industry, and maybe just on a high level, the pros and cons of each one?
Mm-hmm. Sure. Generally, what happens with crack management programs is at some point either through a Hydra test program that's used for integrity management or an inline inspection tool program for integrity management, we're going to have to figure out how many cracks we have in the line and how deep they are and how long they are and how they're distributed. And once we've got that information, or we've got some assumptions about that information, we're going to use one of the various crack assessment models to calculate what is a predicted failure pressure. We want to make sure that our maximum operating pressure is always going to be lower than that, and we're typically going to put in a safety factor. In Canada of 25%. In the US, they work with some different numbers. So it's really important to be able to come up with a failure prediction model. Now, if you go shopping for a model, you'll find that there are actually quite a lot that are available. And I put them into sort of three broad buckets. The first bucket is the log secant models. Back in the late 1960s and early 1970s, there were log secant models that were developed by the Fadhel Institute in Columbus, Ohio. And what they do is they basically take sort of elastic plastic behavior, they roll it together, and they've got a simple one-line equation or two-line equation that helps you predict what your failure pressure is going to be. Now, back in the 70s, there were two models developed. One that was for through-wall cracks, and that's sort of looking at leak rupture boundaries. And then the second one was for surface cracks. The one that's for through-wall cracks, the validation work turns out to be right on the money. It's actually a very, very accurate, very precise model. The developers that came up with the surface crack model, what they found is it was overly conservative. It's about 10 or 15% overly conservative. And I think, like you mentioned, we're going to talk about that quite a bit more tomorrow. But what the developers did in 2007 or 2008 is they came up with a modified log secant model where they added an extra term to try and account for the issues associated with the original log secant model. So those models have been around for 50 years. To my knowledge, the through-wall crack model is the only one really used by industry. The original and modified log secant models are considered to be kind of dated, so they tend to be put aside by most operators. The second bucket of models we can look at is the failure assessment diagrams. And these are the models that you'll find in, say, API 579, Chapter 9. You'll find this in the British standard. You'll find this in European standard R5 or R6 or whichever one it is. And you'll find it in PRCI's latest model, the MAT8 model. And with this, rather than the log secant models where you sort of have elastic plastic behavior kind of buried into the same math, with the failure assessment diagrams, you're actually doing two separate calculations. One is a brittle fracture calculation, where you're comparing your stress intensity factors to a toughness. And then the other one is you're looking at ductile failure or plastic collapse. And what you do is you do these two calculations independently, and you plot your points, you plot your results on a failure assessment diagram. The failure assessment diagram is a plot of basically fracture toughness on the x-axis and yield strength on the y-axis, and there's a line that you have to stay under. With the failure assessment diagrams, you have to satisfy both your brittle fracture and your ductile failure models in order to be considered safe. So there's kind of four options to choose from there. The third bucket that's really available to industry right now is Corlas. And Corlas is a bit of a different beast. It's also got two calculations. One of them is a ductile failure calculation, which really just mirrors something like ASME B31G or R-string. So it's essentially like a corrosion model. It's like a blunt flaw plastic behavior model. The second one that they have is a brittle fracture model that's based on calculating a J integral for your crack. So a J integral is sort of a different way of doing things. It's based on energy absorbed at the crack tip during failure as opposed to stress intensity. So it's kind of a different beast. Now with Corlas, you do the two calculations independently, and then you choose the lower bound of the two answers you've got. That's kind of an interesting thing because essentially, depending on your crack length and depth combination, and particularly depending on what the toughness is you select, you're going to have your answers come out of either one bucket, ductile failure, or the other bucket, brittle fracture failure. So the agreement of the data to those different models is really, really sensitive to what types of flaws you're putting in. if you're putting in stress corrosion cracking flaws that tend to be longer because of interlinking, you're going to tend to fall into the ductile bucket. If you've got short flaws with very low toughness along a long seam and it's a fatigue issue, it's going to be more likely to fall into the fracture mechanics bucket. So those are kind of the three categories. And as you mentioned, tomorrow we're going to talk a little bit more about this. I've kind of looked at the theory behind these models, and I have a few kind of question marks. And so I've been developing my own model, which we'll talk about in more detail tomorrow, I guess. But that's what you've got to choose from on the assessments there.
Excellent. So, you know, you mentioned a very interesting point, and I know a lot of companies struggle with this. Can you talk to us a little bit about toughness and how companies can go around maybe estimating or guessing, or maybe is it tables? What maybe testing techniques? What could guide companies to select accurate or close to accurate toughness values?
This is the $64,000 question. Toughness tends to be a very, very tricky thing to measure. And one of the key things that makes it tricky to measure is a lot of the time we're worried about the toughness of the long seam weld, and the long seam weld is by definition you know, going to be weaker if you have a lot of defects in it, if you didn't do a good normalization program during the weld and that sort of stuff. So toughness is one of the challenges that we fracture mechanics people work with all the time. Now, the quickest and easiest thing that we can do in the business is to look at the Sharpie toughness test. So if you've ever seen a Sharpie toughness test, essentially you cut a sample out of the pipe. It's probably about as big as your finger. It has a notch cut into it, and then you have a big hammer that comes along and smacks that sample. And when the hammer swings, you calculate how high up it goes on its backswing, and you can calculate how much energy it took to fail that sample. That's a very, very simple way to do things. It's generally going to be done at all the pipe mills because it's a quick and easy number, and people have been working with that for many years. But in the academic world of fracture mechanics, it doesn't quite really fit with anything else that's being done. If you look at the academic world of fracture mechanics, you'll see K1C toughness tests, and those are typically done with what's called a compact tension specimen. A compact tension specimen is probably about the size of my little notepad here, my little sticky pad. You put a crack into it, and then you basically, why don't I do that? Okay, I take my little, don't worry. I take my little compact tension specimen and I just pull on it. And at the point at which the fracture occurs, you can back calculate what is the critical stress intensity factor that caused that failure. And the stress intensity is based on the stress applied and the square root of the crack depth. And then there's some correction factors for geometry. Strictly speaking, the stress intensity factor approach is really essentially was developed for brittle fracture. And sometimes we have to think about elastic plastic behavior, particularly with steels. And so there's another test that you can do where rather than calculating the critical stress intensity factor, you calculate what's called the critical J integral. The J integral approach is related to the K1C, but what you're doing is you're looking at how much energy is absorbed during that failure. And that energy absorbed is not just from the fracture, but it's also from plasticity that occurs during the test. So it kind of gives you something a little bit different to work with. The trick with those K1C or JR curve tests is that they're a lot trickier to do. You can't just pull out a sample and whack it with a hammer. You have to have very, very specialized equipment. So you'll see that in the national labs will do that. You'll see that at all the universities, and you'll see that in all of your fracture mechanics textbooks. It's it takes quite a bit more effort to get a number. Those are kind of the two basic ways to do things. And there have been a lot of analysts that have taken their Sharpie data and they've taken some JR data based on the same material and then tried to correlate them. So sometimes you'll hear about the Wallen correlation, which will correlate if you have a Sharpie test and you want to know the equivalent J integral test, you know, what's your answer going to be? Or you might hear of the Ralph Novak test. same sort of deal. You're trying to convert your Sharpie test into a K1C value. Those are two models that you'll find in, say, API 579 to give you an approximation. Now, in the pipeline business, we struggle with what's the toughness of a given section of pipe. We might have a 50-year-old pipe and somebody lost the QA records from the mill, and there you've really got two options. One is to cut out a section of pipe and take it to the lab and do a test. Or there's a group, they're called Massachusetts Materials or something like that, a group out in Boston that has come up with an in situ toughness test. And it's considered to be basically non-destructive. Essentially, they've got a small tool that scrapes the surface of the pipe. And as they scrape the surface of the pipe, they measure how much force it takes to cause that scrape. And then they can then infer a toughness from that. That's a tricky one, though. It's as far as I know, that technique is, sort of largely experimental. Given that welds tend to be really heterogeneous, it's very rare to get a nice even test. So, toughness is one of those things where we come up with the best answer we can, and then generally lean towards a lower bound value just for safety.
Yeah, and so you were mentioning also the different types of SCC there. Just to backtrack a little bit, I just wanted to get your thoughts on, even if it's on a high level, but you often hear talks about the different soil types, so clay versus loose gravel, and how does that affect SCC susceptibility when one is doing a study on the different areas that might be susceptible to SCC?
Yeah, that's a good one. That's a good question. There have been studies done that show that some soils are more susceptible to SCC and some soils are less susceptible to SCC. Generally, when you read these, it's like you're reading a geology textbook because people come up with all sorts of crazy words about how to describe the soils. I'm probably not the best person to talk to about that. There are some pretty smart soils people out there. My understanding is it comes down to a couple of different things. If you have a very fine soil like a clay tends to be fairly hard packed, and you don't get water moving through it easily. If you have a very sandy, gravelly type soil, it's going to be a lot looser packed, and you're going to tend to get moisture moving through that quicker and easier. The second thing to think about is different soils will have different salts in them, depending on what sort of cations you've got and what sort of anions you've got. That's going to affect what your stress corrosion cracking mechanism is. And again, I'm not a super duper electrochemist. There are probably some smart people out there that will tell you which different chemicals have a bigger effect. And then, of course, depending on how many salts you've got, and depending on how dense your soil is, and resistive your soil is, that's going to affect your cathodic protection system, right? You can turn on your rectifier, you can have current going to the pipeline, but depending on what type of soil you've got, that's going to influence what's the potential that's being felt at your pipe surface. So there's a lot going on there. There's a I didn't mention this before, but another technique you can look at to manage stress corrosion cracking is to do a direct assessment. And if you dig around, there's a NACE standard out there. I'm going to say 224 or something like that. And what they do is they go through a list of various factors that influence stress corrosion cracking, and they say, for any one of your pipelines, take a look at this list, and it helps categorize whether you've got a big problem or a small problem in different regions. And that gives you a chance to sort of target really problematic areas of your pipeline, allows you to go out and dig and see where stress corrosion cracking might be prevalent. I think it's the NACE standard is one of the really good ones. You'll also find a couple of other documents out there floating around. SEPA did a very comprehensive report about 20 years ago. So if you can find that, it's got some very detailed work in it. Or PHMSA sponsored a report, again, 15 or 20 years ago, Technical Task Order 8. I believe it was a Michael Baker report that was sponsored by PHMSA. And there they go through a long laundry list of all the different factors that come into play. So it really gives people like you and me a lot of things to think about. And yeah, it's not easy trying to figure out what the key variables are. And yeah, we do the best we can and go safer when we need to.
Perfect. Yeah. let's move on to inline inspection capabilities and tools. So, we talked about crack models, we talked about susceptibility. Let's say a company does a risk assessment, and of course, going down the pig and dig pathway as a form of handling a program or managing a program. So, what are the different types of tools, inline inspection tools we have to inspect the lines? I guess there's the liquid side, so the ultrasonics, and then there's EMAT on the gas side. So
Mm-hmm.
can you talk to us a little bit about that? And then a little bit of course, promises versus reality, because of course our ILI friends, promise us the world, which is, part of their job, of course, but, what really can be understood from the results, and what really can they provide for us?
Sure. Okay, so when you talk about a pig and dig program, for some of the younger viewers, they might not have heard of that. Pig is a nickname for an inline inspection tool. So an inline inspection tool, think of it like a sort of a robotic snake that's a little bit smaller than the pipeline diameter. It fits into the pipeline, it gets pushed along by the product pressure, and it does an inspection of the pipeline from the inside. Now, these inspection tools will have a computer on board, they'll have a battery on board, they'll have driving cups on board, and then they'll have, in the case of a liquids line, they will have sensors around the outside, ultrasonic sensors. And what these ultrasonic sensors do is they're sending out a sound signal. They're sending out a ping. I like to think of it like I'm watching one of those old submarine movies where the Americans and the Germans or whoever are trying to find each other, and they send out ping signals, and they're listening for an echo to come back, indicating that there's an enemy submarine. Same sort of idea with the pipelines. If a tool sends out a ping, it gets into the wall of the pipe, it basically bounces around the wall of the pipe, and if the pipe is in perfectly good condition, that sound energy will just bounce around and dissipate. It will attenuate, and you'll never hear the sound again. However, if there's a crack in the pipeline, when you send that ping signal into the pipeline, it will hit against a crack, it'll bounce back and be heard by the ultrasonic sensors, right? And so the computers on board will read that signal, and they'll say to themselves, well, at this particular location in the pipeline, at whatever orientation, we got a signal return. And that's indicative that there could be a crack there. Now, one of the things we have to think about is we can't say 100% definitively that there's a crack, right? We had a sound signal. We had like an echo response. So what the ILI vendor technical staff do, and I'll tell you, some of these people are, the smartest people you'll find in industry, is they take a look at all of those sound return signals, and they've got various algorithms, and they study physics, and figure out which one of these sound signals is most likely to be an actual crack. They have sound signals coming from one side, they have them coming from the other side. They'll cross-reference the clockwise and the counterclockwise return signals. And depending on the timing of the return signal and depending on the amplitude of the return signal, they can say with pretty good confidence that they have a crack there. Now, what makes their job really, really challenging is a crack is not the only thing that's going to reflect the sound back. If they have a weld offset, so if they have a section of pipe where the welding didn't quite line up properly, then they're going to have these little corners in the pipe that can reflect sound and give them some confusion. I think the vendors are pretty good at sorting that out. You can also have some unusual laminations or something in the pipe that reflect sound, and that means that the analysts have to think a little bit harder about how those sound waves are bouncing around. Typically, when you get an inline inspection report, the vendors will tell you that they have a sizing accuracy of, say, plus or minus 1 millimeter deep, but they'll say with a confidence of, say, 80%. So they know that things aren't perfect. They do the best they can. Quite frankly, I think it's amazing that they find the cracks and size them as well as they do. But there's always going to be just a little bit of uncertainty in there. The ILI guys are constantly just sort of twisting their little dials and trying to dial in their algorithms to get them better and better all the time. And so, you might see one tool is plus and minus a millimeter with 80% confidence, but then, a couple of years from now, they'll do the same with 90% confidence, right? They're getting better and better as they understand more of what's going on. So that's kind of the basics of it. You mentioned that with the we've got a difference with the liquids lines and the gas lines. And where that comes into play is with the liquids lines, we can send a sound signal through the oil, but with the gas line, it doesn't quite work. The signal just gets scrambled. And so there's another tool called an EMAT tool, which is electromagnetic acoustic transducer. I'll have to look that one up.
Yeah. Transducer.
Transducer.
Yeah.
So what happens with that is it's kind of like a touchless technology. You don't have sound wave that's going through the gas. You have an electromagnetic signal that's generated by the inline inspection tool, and that causes sound waves to be induced in the pipe wall. So it's a little bit of a different technology, and my understanding is it's quite a bit more advanced technology than the basic ultrasonic tools. Those EMAT tools are typically used by the gas people because they can't rely on the ultrasonics, the basic ultrasonic tools like the liquids peoples can. So yeah, two different types of technologies. I haven't really done a lot of work with EMAT. I gather it's a challenging technology to work with just because of the physics involved in it.
Yeah, no, that's perfect. Thank you for that. So, we have our inline inspection tool understanding, we have our crack model. Maybe if we can just walk through a quick scenario, let's say we have a line that's a first time inspection for cracks. How would you say an operator can best prepare and be ready for, inline inspection results from a crack run? So it's let's say, just inventing some numbers here, a 12 NPS 12 pipeline, let's say just regular 7mm wall thickness. It doesn't have a history of Hydra test. Just maybe on a high level, if you could walk us through, you run the tool, you get the results. What could a operator do to be prepared to get maybe bad results? If they know they've cycled it a lot, they know it's tape coated. Just walk us through what that could look like.
Well, typically when an operator decides that they're going to do an inline inspection of one of their pipelines, they're going to go and talk to the vendors. And each different company will have different vendor choices. There are some considered better for some things and some considered better for other things. The ILI vendors are very knowledgeable and experienced on how to set up their tools. So what they're going to need to know is, are you looking for cracks along the long seam? Are you looking more for stress corrosion cracking? In some cases, there are situations where you might have a pipe that has corrosion on it, but because the corrosion is very steep-sided, like pitting corrosion, that can fool your tool into thinking that there's a crack. So operators would be smart to sit down and talk to their ILI vendors and figure out what are the problems that they're expecting to find on their line, and then that helps the inline inspection tool vendors figure out how they're going to calibrate their machine, how they're going to dial in their little their amplitudes, their signal, whatever the hell they do, and kind of leave that side of things to them. Now, the pipeline operator is going to have careful control over the pipeline while the tool is in the pipe. The tool needs to run at a certain speed to get the best results, and that's going to mean that the operator is going to have to probably dial down the pressure for the 2 or 3 days or whatever it takes for that inspection to be completed. So that's one thing that they'll have to think about. The inline inspection tool vendors will then, they'll finish the tool run, they'll download all the results, they'll have their analysts look at all the data. Typically what the ILI vendors will do is they will look for what we used to call at Enbridge a priority notification, where they find a crack that looks so bad that they need the operator to know straight away that there's a potential problem, in which case the operator can either drop the pressure or go and do a dig. Once they've sort of found the really nasty stuff, then they go through everything else in detail and they check their algorithms and they come up with a crack length and depth for each one of the features that they find. They'll send that report to the operator, and then the operator is responsible for choosing one of the crack detection models, taking a look at all the flaws, and first of all figuring out, is there anything that's a failure threat right now or imminently, in which case they might have to shut down the line or go and do a very quick repair. But then they'll also use they'll do a fatigue crack growth rate calculation using the Paris law, and they'll try and predict for each one of those cracks, how long is that crack expected to survive based on pressure cycling in the pipe. So it's probably a good idea for the pipeline operators to take a look at their pressure cycling for their line and try and figure out whether it's potentially a bigger problem, in which case they might have to have a shorter reinspection interval, or maybe their cycling is not too bad, in which case they can expect a longer inspection interval. Now, one of the things that gets really tricky is once you've done your assessment, you have to decide, how to act on it. And your decision on how to act on it is going to depend on a lot of things. It's going to depend on what's the pressure that your pipeline is running at. Is it a high pressure? Is it a low pressure? Do you have any flexibility in your operations? And then you also have to look at your dig budget and say to yourself, how many digs can we afford? If you can afford a lot of digs, have at it. If you can't afford a lot of digs, then you're going to have to look at ways to reduce the pipeline pressure. So a lot of different things to deal with. And in my mind, you always have to have your brain in play when you look at these assessments. Sometimes things can catch you by surprise. So, for example, I came across a situation one time where there was a pipeline operator. They had just done their first ever inline inspection crack detection tool run of a 200 kilometer line that was probably 50s vintage or something. And the ILI vendor came back and said, you've got 50,000 reportable features. So, well, this is obviously a big worry. I mean, the whole pipeline lit up like a Christmas tree. So the operator actually went to a consultant, not me, but another consultant. And the consultant kind of went through the program and they said, we're going to assume a lower bound yield strength on your pipe. We're going to assume a worst case toughness. We're going to take all these cracks and we're going to assume that the tool undercalled them. So we'll add a tool tolerance. We're going to assume the worst case Paris law coefficient. We're just going to be safe, right? And they came back and they said, well, you have to do, I don't know, 5,000 digs or something, or you need to shut down the line within the next year. So the operator got into a big panic over this because, I mean, this is their whole business. The line is 60 years old. It's really never had a problem. And they got into a big worry. So I think what happened there is sometimes as engineers, we can get lazy and we can say, well, here are the regulations. Here's the industry standard. Here's my software. There's the answer. But here's a situation where that's not necessarily helping the operator. So I was called in to take a look, and I really thought about two things that I think help the operator. And the first is, if you think about it, a line that's built in the 1950s would have had a commissioning Hydra test. And what you can do is you can use that crack assessment tool that you've selected, whichever one it is, and knowing what the Hydra test pressure is, you can back calculate what is the worst case crack depth that's likely to be in the pipe. You have to make some assumptions, but you can figure that out. You can also look back at your recent pressure history, and you can say to yourself, well, we know we survived to whatever pressure over the last 2 or 3 days, 2 or 3 years maybe. And you can say to yourself, well, we can do that same calculation again and figure out what's the critical crack depth as of 2 years ago. Now, once you've got those two values, you can basically interpolate the Paris law coefficient, and you can figure out what's your worst case crack growth, and then you can extrapolate that, with the assumption that you're going to keep going with similar pressure cycling. And when you do that, you find out you've got several years to play with. So I think that gave the operator some comfort. And then the second thing that I took a look at for this operator really relates back to what we talked about a few minutes ago with the inline inspection tool vendors and their sizing algorithms. If the tool vendors can say we have a depth of plus or minus 1 millimeter 80% of the time, then you can probably say to yourself, statistically speaking, you've got plus or minus 2 millimeters, I don't know, maybe 98% of the time. And then that last 1% at each tail of the distribution represents plus or minus 3 millimeters, right? So I did a simulation and I said, well, if you've got 50,000 features being reported, and you know that 1% of them have been over-reported by 3 millimeters, you know that you've got 500 features in your list that are grossly over-reported. And you know you've got, I don't know, 9% or whatever that are pretty much over-reported. And when you do the math on that, you realize that with 50,000 features, and this only counts if you've got a really big distribution, is I figured out that of those 50,000 features, something like the top 8% of them, you're pretty much guaranteed are overcalls. not because the ILI guys didn't do a good job. It's the nature of the beast that you've got these distributions. So that gives you an opportunity to kind of rethink things and say, you know what, there are 50,000 features. The quick and easy way to do things tells you there's 5,000 features to dig. But if we stop and think and really target our assessment, we can probably achieve a lot. So, my suggestion for the operators out there is, for the whole situation, talk to your ILI people about what their capabilities are. Talk to your operations people and make sure that they've got things under control. Minimize the fatigue crack growth if they can, and make sure that the inline inspection tool has a good run. And then when it comes time for the assessment, be prepared to think about things. Be prepared that if you do have a surprise that's either a safety surprise or a financial surprise, think of how you can kind of sharpen your pencil and do a more careful analysis before worrying about the sky falling on your head. It's you're rarely in a situation of impending doom, in my experience, even if the numbers might be showing you that. Take a breath and stop and think about things.
Yeah, thank you for that. That's a real, I bet that's a story that I'm sure a lot of the viewers will be nodding their heads, vigorously to. It's like you said, it's almost like the laziness point there, where you take the regulations, you look at your models, and you start listening to what you put it through the meat grinder, and then whatever it says, you just believe it, and because that's what the model says, so it has to be true. And like you said, you have to put on your engineer cap, and really question the results, test the results, do the funny look test, and the reasonableness check is just as important as any assessment out there. So
yeah, I'd like to say our job is to be worried about pipeline safety, and that's what we do. And I'm not saying that we should just sort of be cowboy about things, but we have to recognize as engineers that we're not just worried about pipeline safety. Particularly the engineers that are working for pipeline operators, you have a responsibility to the business to say, okay, yeah, we need to be safe, but I can't just go and spend all the shareholders' money because I was too busy to try and think about things. You look at a program at one of the major operators, they could be worth several hundreds of millions of dollars. And if you think to yourself, if you just run through the numbers blindly and you put conservatism in every possible corner that you can, yeah, you're going to blow through several hundreds of millions of dollars. If you stop and think and sharpen your pencil and say to yourself, well, 5,000 digs it doesn't make sense, right? Let's stop and think about this. I think if you do that more often, and I think if you make sure that the models that you're using are not overly conservative, that they're right on the money, it allows you to sort of calculate your way around a lot of issues. And I think some of the pipeline operators, the bigger pipeline operators, could probably save $100 million or $200 million a year by just refining the way that they're doing things. I say this sort of like casually. I mean, it obviously takes a lot of work to know that you're being safe. But when you look at the various conservatism that's built into assessments, typically, it really compounds on top of itself. You look at model error, crack depth error, yield strength error, toughness error. You're typically assuming that your entire pipeline is at MOP, which it's not. As soon as you get away from discharge, you've got a pressure drop there. If your pipe is going up and down hills, if it's at the top of a hill, it's not going to be feeling that pressure. And if you look at the various conservatism that you've got in these calculations, you think to yourself that you maybe have the standard sort of required regulatory 25% over conservatism for safety. I would think in a lot of cases you've probably got 100% over conservatism. I mean, that's a lot. I think that there's probably a lot of cases where operators are giving away 5,000 or 10,000 kilopascals just because regulations, standard, software, let's do it. So
for sure, yeah, like you said, so number 100%, what we do is safety. Like we're a safety critical job basically. So no doubt about it. There's no any compromise on safety, 100%. On the conservatism, for sure, just to add to that, I think the compounding is the right word you use there. Just like compounding interest is what makes people rich. If you have compounding conservatism, you can almost convince yourself, let's just shut off the pipeline and go home, right? Nothing
Yeah.
ever is safe, so you can get to the two extremes for sure.
I was just going to say, if you read, there's an API standard out for crack management, API standard 1176, and there's a section in there where it brings up this exact point. It goes through and it says, well, consider conservatism here, here, and here. But there's also a paragraph that's basically a warning, and it says, don't just throw conservatism at everything, because if you're throwing conservatism at everything, then you're going to be in a panic situation over everything, and you need to think of not how to fix every single problem that drifts across your desk, but you have to think about what are your budget constraints, what are your resource constraints in terms of people, calculation ability, and say, where am I really getting the risk down? Where can I get the best risk reduction per dollar of effort or per hour of effort? Because that's that's a way that you can really refine the way that you're doing things, and not only save yourself money, but by doing that analysis, you can also demonstrate from your risk management. Okay, we've got our green squares in this corner and our red squares in this corner. If we spend $100,000, this red square becomes a yellow square. Okay, we're going to do that. You might find another section where you say to yourself, well, we're supposed to repair this, but it'll cost $1 million, and the green square turns into a green square next to it. Well, that's not really being super effective. So
yeah, for sure. The concept of de-risking the pipe, what actions actually de-risk it, and what actions like you're saying, bang for the buck, have no bang for the buck. So I'll give you the last word here, Colin. Future outlook, the vision for the future. Where do you see crack management going, whether that's crack models? I know you're very involved with that, and we'll talk more about that tomorrow. ILI tools, where do you see crack management in the next 10 years?
I think that right now we're in a very interesting sort of social and political situation with the oil and gas business. If you look at the news every day, it tells you that the oil and gas prices are down, and there's a lot less product being used, and in part that's because of COVID. I mean, you think about COVID, there are a lot less people driving to work. A lot of people are doing the Zoom meeting thing and working from home. You've got a lot less people traveling, a lot less people going on vacation. So the oil and gas business is not doing super well, in part because of COVID. But then you also look at the politics of particularly Canada and Europe, that are pushing towards thinking about solutions to climate change. And one of the things that's looked at is obviously reducing dependency on oil and gas. Now, we can't get rid of oil and gas overnight, because oil and gas is used for so many different things, not just burning fuel, but also making polymers and such. But because of the social and political climate, it's going to become increasingly difficult to build new pipelines. I mean, we know that the Trans Mountain pipeline is hitting all sorts of political and legal hurdles. Enbridge had the Northern Gateway pipeline that was scrapped for, I gather, largely political reasons. We've got the Keystone XL pipeline down south to the US. President Trump likes it. President Biden, if he gets elected, would potentially cancel that. There have been issues with the Eastern pipeline going over to the east.
Yeah, energy.
So it becomes increasingly difficult to build new pipelines. And so what that means is the people that own and operate the pipelines are going to have to look more at getting as much service as they can out of their older pipelines. And that's going to mean that people like you and me are going to have to do extra homework, because as those pipelines get older and older, there's more and more of a concern with fatigue, right? There's more and more of a concern with SCC getting deeper. There's more of a concern with the coatings are disbonding because they're 70 years old, 80 years old, 90 years old. So it's going to mean more homework for us. I think that when it comes to the inspections, I think that the ILI vendors do a great job of inspecting the pipelines. But when you think about it, their hands are tied because they can't physically look at the pipeline. They're not like a mechanic where you can lift the hood of the car and say, okay, let's replace the spark plugs. They're basically flying blind. And the fact that they do such good work and have such good accuracy and detection capabilities, I think is really impressive. But at the end of the day, they're looking at sound waves bouncing around in a pipe, and there's only so much you can do with that. So I see the inline inspection tool vendors kind of chipping away at their various issues and getting better and better all the time, but I don't think they'll ever be perfect. Where I see the avenue is, and this is partly because I'm an analyst, is, you know, the inspection data is limited because of sound bouncing around. We no longer have the benefit of new pipelines that have fantastic long seam welds and fantastic coating and excellent QA. We're dealing with these older pipelines. And like my example, where there was an older pipeline that had 5,000 features reported as being requiring digs, the business can't operate that way. So I see more effort in really fine-tuning some of the assessments that we're doing, thinking about where the conservatism is, sharpening our pencils, and saying to ourselves, where are the problems more likely to be? You can't just fix absolutely everything. You have to target what you're going to spend your money on and what you're going to spend your time and resources on. And I think that there's possibly a lot of savings there for the companies. And I think that a lot of the companies are going to be looking for those savings because they know they can't build a better pipeline. They know that they've got to get as much service as they can with what they've got. So maybe that's just me being an analyst thinking along those lines, but that's where my head is right now.
Excellent. Well, thank you so much, Colin, for coming on. Again, we'll talk again tomorrow for part 2. For all the viewers, please stay tuned for part 2, where we will discuss Colin's GEM model, so the gamma exponent model, right? So thank you again, Colin. And if people want to reach out to you, maybe you can talk to us a little bit about your YouTube series, as well as is the best way LinkedIn, and then with a message that so that it's not a random connection.
Yes. If anybody has any questions about what I've talked about here or what we'll talk about tomorrow, you can contact me through LinkedIn. I should be fairly easy to find. There might be more than one Colin Scott, but there's only going to be probably one that's connected to Hussain here. So if somebody wants to contact me through LinkedIn, that's great. I would suggest that you write a message saying that you have a question about the PI show or my GEM model, just so that I know that you're not just some random person trying to sell stuff. I check in LinkedIn a couple of times a week, so I'll try and respond to your questions. And like you said, we'll talk tomorrow about my gamma exponent model that I've been developing for the last year or two. I've actually got several videos that I've put together for YouTube, so we're kind of in the same space here. And anybody that wants to see some of those and get a heads up for our next meeting is just do a Google search on pipeline integrity, either gamma exponent model validation, or I have a series that's called Things That Make Me Go, where I scratch my head and I think about the theory that we're going to be talking about tomorrow. So yeah, I'm certainly glad to answer any questions. You can probably guess that I like talking about this stuff and come up with new ideas on how to make the pipeline industry a lot better. So before you go, I'd like to say thanks. Thanks for inviting me onto the show. It's good to talk about stuff and get some questions that make us all think about how we can do things a little bit better. And I look forward to keeping an eye out for listening into the show for some of your other guests who I'm sure have got all sorts of things to learn from. So thank you.
Perfect. Thank you again, Colin. We will definitely put down in the link below a link to your LinkedIn page as well as to your YouTube videos there. And again, we'll see you tomorrow to talk about the GEM model. And then for all my viewers, thank you for tuning in and take care, and see you for part 2. Thank you again, Colin.
Thank you, Hussain.
Hey everybody, welcome back. Hope you enjoyed that interview. Please remember to like, subscribe, and share. And until next time, keep on pigging, digging, repair coating, and backfilling. Take care.